I know it's tough, everybody's really busy and tough to give up time, especially on your Saturday, share time with your son and Johnson, Andrew, you guys driving up here to see us. Thank you very much. It's a really big thing to us, and we really do appreciate it. Today, we're having our conceptual design review for our 2014 team, and that is, we're going to look at several of our subsystems. I'll let them go ahead and start in just a second. The thing is I want you to remember that we're changing things up and that we are one team here. We no longer have maroon and orange and that kind of thing. We're one team, and we have all of our students, even our volunteers, all contributing to the competition car. Okay, freshmen, sophomores, and of course our juniors and seniors are working together as well. And so what we've tried to do is foster an environment and a working team so that we're each of us contributing, taking on and putting our expertise and skills and time into the different projects. And so what we're trying to spend a lot of time on communicating with each other to help each other out. Hey, these are the issues we got. We think maybe you guys can start improving on that. And that's where we're going with the things that we're doing, okay? So, as we go today, we're going to go on a format of, roughly speaking, each one, an overview, the sub-teams. Each of the sub-teams will present on the subsystems. All right, we break everything into subsystems these days, and that's a good thing. But they're going to speak to that, and then, of course, our teams are organized along that front. Each sub-team has about 15 minutes, and then we'll have 5 minutes for questions, roughly speaking. If we have more involved discussion, we can, of course, do that afterwards. Okay. So, but I would like for we're asking for all the help, help and insights that you've got, but also constructive criticisms. Okay. So please, Hannah, go ahead and let's get started. We'll go from there.
In our conceptual design, and we have also helped out the seniors with their combined design binders. In the spring, we're trying to get 75% of our whole design done so we can start manufacturing pretty shortly after we get back from summer break. The 2014 car is an evolution of the 2013 car. So rather than doing everything from scratch, we're working off the 2013 car and trying to further develop it. So what does it take to be successful in Winter, Michigan? We predicted the performance that we need to do well in Michigan and win the competition. How you can see here, this is a line that was used to forecast the skip pad event winners. It takes the top 5 average of the 2012 results, and the black line you can see is the linear regression of the event winners. In 2012, the top 5 average was 5.4 seconds. We did the same for the acceleration event winners, so you can see again the top 5 average, and the 2012 results show that it was 4.21 seconds. Out of those graphs, we developed our overall dynamic goals. How you can see our skip pad event is 0.4 seconds faster than the overall average. That is because we don't just want to do well, we want to win competition. And this is what we think does it take to win. Same for the acceleration results. One of our main goals is to finish endurance. And we don't just want to finish endurance, we want to do well on it as well. So these are our overall program goals. We want to maintain a professional team interaction. We want to have a schedule, and we want this to be fun rather than something not fun that we have to do. We want to make design finals. We need full documentation at design finals so we can bring forth our design and do well on that. We want to keep on working on sales and costs. Therefore, we want to get industrial engineers in here, communication majors, business majors, and so forth. We want to reduce the driver dependence on the car, get a driver training program started, and all that stuff. We also want to test the car a lot, at least 50 hours before competition, so we know how it works. And we think this is what it takes to win competition. I'm now giving up to Tyler and the engines.
morning, everybody. We're the engine sub-team. We have Dan on intake, Matt on exhaust, Kang on fuel, John on oil and cooling, and I'm Tyler on engine tuning. We are going to implement the third consecutive successful WR450 single-cylinder engine package. We're going with this engine because we are iterating off a strong experience and knowledge basis that we've been working on the past few years. To make these gains in performance, to iterate off of this design, we're going to work on an integrated dynamic model of the entire subsystem so we can analyze a full cooling loop, an airflow control volume, as well as engine output. This is going to allow us to optimize all of the subsystems within the engine subteam and make the power that is necessary to handle the increased loads from the aerodynamic package that we'll be adding. I believe it's imperative that we update the engine, something 2007 and newer from the WR series. 2007 is the year Yamaha implemented a myriad of changes and upgrades to the WR series. It includes a new balancer, a new case, head, a piston cooling jet, and it integrates an oil tank. In 2012, they also added stock fuel injection. So if we're fortunate enough to come across 2012 or a newer engine, we'll certainly accommodate for that. We'll be using the Motec M400 ECU unit. We're planning on taking further advantage of this and having a dedicated ECU engineer that will know the inner workings of this system and coordinate with the traction control and electrical sub teams to take full advantage of it. This ECU focused person will also incorporate underclassmen and build and foster a working knowledge with sophomores and freshmen, because we're not going to have a ringer coming in that knows the workings of Motec, and this is a kind of a mysterious system, so we're going to have this knowledge basis and lay the groundwork for future teams. We've made great advances in the dyno this year, and we're going to continue to do that. We have the whole dyno room to ourselves now. The electrical system has helped us clean up the wiring. We plan on having, in the next couple weeks, updated LabVIEW VIs to help us out with the software. We'll have a complete second engine package set up in the dyno that will be modeled exactly as it will be on the car. We'll have identical geometries on the runners and identical connections and links in the wiring. We're going to use this facility to an abusive extent. We have it to our disposal, so we'll see all the issues that will arise from this engine. So when we inevitably have trouble on the track, we'll have seen the problem before and we'll know how to diagnose it and address it.
So for the 2014 induction system, the biggest change we're looking into is the side intake to introduce a ram air effect. With the entrance of the intake facing directly into the flow, it should increase the velocity and in return increase the pressure in the runner and plenum. We're also sticking with the butterfly throttle valve from the 2013 team. It is shown to be the best choice over the needle valve, the slide, and the roller throttle. In terms of manufacturability, adjustability, cost, weight, and things like that. We're going to continue to rapid prototype our components from Stratasys, but we're going to look into decreasing the wall thickness of the components to decrease the total weight of about 5%. But we're going to stick with the internal bell mouth, the trumpet at the throttle body, and the tapered runner because those have shown to increase our flow rate.
An objective of the engine exhaust is to make sure that it's reliable. This means that the car needs to be under the required decibel of 100. And it also needs to make sure that it has a strong fatigue light. I need to make sure that cracking does not occur in the muffler due to vibrations and stresses caused from mounting it. I also need to make sure that it has the correct frequencies to make sure that it has a low back pressure, which will allow for more exhaust gases to come out. In order to do this, we will plan on using a stepped primary pipe, and this will create, because of the step and size of the primary pipe, it will create two resonant points, which will allow for more times to bring the exhaust gases out. And after doing this, I will find a muffler with the correct diameter that will allow for airflow to make it more effective. And I also have to look into it being a low weight.
Good morning, guys. I'm going to talk about the fuel system design. So the first thing I want to talk about is the fuel tank. So the tank design, what I'm designing the tank for is to reduce the sloshing and reducing the weight. So one of the way before I start designing a tank is I want to understand how the sloshing acts in the tank. So if a car is accelerating and a car is cornering, and I want to see how those forces make the fuel inside the tank slosh. So one of the way I'm going to do that is I'm planning to simulate a very simple tank such as a cube, and then see how the fuel is sloshing that after simulating the force acting on the fuel. And then another thing I want to talk about is how I'm going to reduce the weight. So right now I'm looking at two materials right now, the high density polyurethane and the aluminum. So some of the benefits that with high density polyurethane is that it is lighter weight and it is more chemical resistant. But some of the cons to the high density polyurethane is that we don't have a lot of experience manufacturing it, and we also, the cost of it, of manufacturing is a lot higher, because some of the methods that are used to manufacture it is blow molding and plastic welding, which I'm sure we're not capable of that in shop. And as for the aluminum, we have a lot of experience with using aluminum right now, and the cost of the aluminum, or the cost of manufacturing aluminum is not as high as the HDP polyurethane, high density polyurethane. And the strength to the weight ratio of aluminum is also pretty good from what we understand. And after I select the material, I want to look into how we're going to mount the fuel tank. Because in the past years, we know that the fuel tank cracked because of the stress and the strain that a car exerts on the tank. So one of the solutions that I was looking into was the spring mount right there. So one of the way that this mount works is that you mount the fuel tank onto that mount, and you mount that mount onto the car, so that the spring in the middle can dampen the force that a car exerts onto the fuel tank. And for the fuel injector, one of the things that came up in my research is that the injector location could also play a role in the efficiency and the power performance of the engine. So one of the things that I want to mess around or research more on is understanding how does the location of the injector relate to with the vaporization. Because if the fuel vaporizes too fast, then it displaces the oxygen so that the combustion is not as efficient. But I want to see what is the optimum distance between the intake valve and the injector location to increase vaporization without displacing the oxygen. Next thing I want to talk about is the pressure in the fuel injector. So right now we're running a single pressure regulator. So I want to see if we can increase the pressure to see if that improves atomization, which could then improve power and efficiency as well. So but before I want to change into a different pressure regulator, I want to make sure that the reliability is still at a good safety of factor, so that our car does not fail in competition. So I'll have to justify, is the performance gain enough to outweigh the reliability?
So for 2014, we're looking into getting a new WR450 engine. The 2007 engines come stock with a fully integrated oil system. It's dry sump. We plan on running it stock. It's an improvement from previous years where they ran a semi-dry sump. The dry sump, there's advantages to it. There's no oil pan, so there's no sloshing. It limits aeration, and you get consistent oil pressure. We'd have to ensure that we have no starvation, because we're not running it it's a dirt bike motor. It's built for a dirt bike. We're running it in a formula race, so it's not built for that. We can test to ensure that there's no starvation in some of the extreme events like skid pad. But we've seen this system run successfully in Michigan before, so that's why I plan on running it stock. For cooling, we're just going to iterate from previous year designs, make sure it's reliable, no leaks. We want to maintain a 180-degree engine temperature. We'll size the radiator for our engine thermal output, as well as the fan. We need the fan to help assist in cooling during times of like driver changeover in the endurance laps. An improvement we're looking to make is an aftermarket impeller. The aftermarket impeller improves coolant flow from a stock aftermarket impeller. This would also help us with the solve the problem of overheating when we're doing the driver change and endurance because of the increased coolant flow.
So a big push forward for the Formula VT Motorsports program in general is a dynamic model of the entire system. So with the engine, we're going to focus specifically on integrating Ricardo Wave and MATLAB and Simulink. This is going to really help us with our model-based design as well as laying the groundwork for the rest of for years to come for the Formula program. This is going to allow us new levels of precision when we're optimizing these engine parameters, the runner length and the cam profiles. This is going to allow us to make an inertial model as well as the engine output, model the engine outputs. So we'll be able to simulate this within a sim driveline with the modeled suspension and driveline subsystems. So we will, with the inertial model, we'll also be able to model for vibrations and further our vibration analysis and communicate this data to the suspension team so they know how to work with our outputted frequencies and forces, as well as with the ergodynamics team and human factors, so they can damp the response and make it a more drivable and user-friendly vehicle. As far as tuning, we're going to use our perfected Ricardo Wave model to optimize our cam profiles. The custom or aftermarket cam profiles or grinds could cost upwards of $500, but I believe there's a potential to gain 7 horsepower here, and that's a worthy endeavor. We can also experiment with coefficients of friction and geometries within the cylinder head and decide whether porting is a viable and gainful pursuit. And if it is, we can later test this with the previous heads from the older engines and fluid testing. Like I said before, we're going to take full advantage of our Motec. This is going to allow us to utilize our fully instrumented engine. We're going to have a full sensor array on both the dyno engines and the in-car engines, and having this sensor feedback will allow us to ride predictably and optimum performance, whether we're in Blacksburg or Michigan or Nebraska. This is also going to help us with diagnostics. So here's an estimated cost. For the engine cost, this is estimating for one new engine with some sell-back value from the rest of the bike if we buy the full bike. In the spring, these are our rough plans. We'd really like to pull the trigger on buying this new engine, especially during the down season, during the winter, if we can find the money. We're consistently working on improving these computer models and simulations, taking advantage of the seniors now and learning from them while we're in the dyno. Develop our subsystem test plans and how we're going to implement these in the summer and future. Helping out with 2013 and getting the 2013 car up and running and prepare for our preliminary design review at the end of the spring. Questions, comments?
All right, I'll start. You want to go back? You want to go through the slides, or do you want me to just ask questions?
We could.
Want to start? I'll do the easiest.
We've only got 5 minutes.
A few quick questions. All right, go to the next slide. So, have you looked back at some of the previous designs that we've already done for the 450 for the intake?
I know 2009 or 10 had a ram air.
Yeah. So one thing to consider is that the volume of your intake doesn't necessarily, you don't have streamlined flow through the intake like you would on, say, a larger cylinder count engine. The volume of the intake pretty much acts as just a reservoir. So the throughput of ram air doesn't necessarily help you unless you actually are having starvation issues with pulling air back into it.
Okay.
I just know there's also packaging issues with that.
Yeah.
Pretty tough. Keep going.
Actually, can we go back to that? Or it's kind of with the next slide too. Look at how both exhaust resonance and intake resonance affect the cylinder pressure, and even start with the basics of how two-stroke works and why everybody runs expansion chambers on two strokes. We had some driver complaints last year about drop throttle responsiveness, and the car was still making power after the driver was getting off the throttle. And these are very quick events. It's not like he gets off the throttle and 3 seconds later the engine's still pushing him. It's a couple tenths of a second. And whether a ball plenum is still the best way to go. And also just do a quick hand calc on whether the ram air intake effect is actually worth something, because at least in the Formula 500 community, that's heavily debated at 120 miles an hour if it's doing anything. So that's not necessarily to say that it's not going to work, but at least in some cases it doesn't always work. So make sure your situation will work for it. Okay.
I've got a question on that slide too. You guys, you mentioned the decreased wall thickness of your manufacturing. Realistically, how much do you think that you'll probably gain in a weight savings by reducing the wall thickness, and how do you think you would do that on your RP model?
Well, initially the RP, the main thing looked at was just the geometry of the models. The thickness wasn't really taken into account. So if there's any way I could just go back and actually take that into account of the design, possibly looking at 5 to 10% decrease in total weight.
One of the things that we often forget when we're thinking the big picture stuff is that, and we did it back eons ago when I was here, is that we looked at going from 035 to 028 or 060 to 040, and the manufacturing got so difficult and so tricky is that every weld or every ply that we took off was.
I'm working on rotating components. The parts we have with the rotating components, you have half shafts, hub stubs, and then wheel inners and outers. Our design goals, first most, we have reliability, obviously. You need to design for fatigue and wear. The rotating components probably see more wear than any other components on the car. So we need to design for them and make sure they don't warp or lose their efficiency in any way while we drive it. And also we need to design for failure. We don't want our parts failing, obviously, while we're driving, because that could be obviously a big safety issue. We also want to improve on driveline efficiency. We want to lower weight and lower the mass moment of inertia in any way we can. Obviously, lowering weight is a big thing throughout the car, and especially on rotating components. But we don't want to lower the weight or improve the efficiency of any of our components while compromising the reliability. So it's definitely important to pick the right materials and the right size of the different parts. Here's some new design ideas we have. Looking into carbon fiber half shafts, which is a thing we've looked at in the past and just kind of went away from because they're not easy to implement. The pros, you have lower mass, higher specific stiffness, higher fatigue resistance, and higher specific strength. And you're also quite easy to mold into whatever design we choose to make with them. That's a big pro with it. But it also comes with a lot of cons. They're brittle, unlike materials we've used in the past. It's not like steel 4340 where it will yield before it breaks. It's going to break whenever it breaks, and that can be a really big safety issue. They're also quite costly, just like with any material. When you lower the weight, it's going to be more costly than material we've used in the past, but it's determining whether that performance gain is worth the cost. And probably the biggest con is the attachment. You have to, it's not an attachment like we have in the past where it's steel on steel and it's easy to attach them. You have to use some kind of resin or epoxy to attach them. And when you attach aluminum with carbon fiber with epoxy, you get galvanic corrosion, which is which is not very good. Because the resin acts as an electrolyte, and it can cause the bond between the aluminum and the carbon fiber to weaken, which obviously could cause some failure, and that's something we definitely have to look into. But there are ways to get around that with putting some kind of material in between the aluminum and the carbon fiber. Other teams have used fiberglass sheets. So it's definitely something we can look into. Another design idea is integrated hubs. It's something we did in 2011. It obviously, the pro is it removes a part from the driveline, it turns two parts into one, which is obviously a pro. It simplifies the system. But it comes with changing the upright significantly, but with the new aero package being attached to the uprights, we'd have to change the uprights anyway, so it's possibly a good way to re-implement the integrated hub at CD. Another idea is the carbon fiber or magnesium wheels. Right now, the 2013 team's looking into carbon fiber wheels. If they go ahead with that, that'd be great. But obviously the pro is lowers mass, but it comes with a high cost. So obviously, I don't know a whole lot about magnesium wheels, but either of those would be good design solutions to lowering the mass of the wheels. And then here are some graphs just showing some comparisons to aluminum, steel, and then composites. Different for them.
For the 2014 shifting, we're going to stick with the electro-pneumatic shifting system. The parts of it are the transmission, the pressure vessel, the actuators, and the solenoids. Our objective, as with the whole team, is reliability first. So with the new engine being purchased, I'm going to reevaluate the forces it takes to shift, which then determines the pressures in the lines. And also I'm going to do a fatigue design on the clutch cable, as we've seen it fail in the past. And also trying to eliminate any leaks in the line. Also, I'm going to continue the simulation of the driveline, as Alex has worked on, and use that to reevaluate the optimal gear ratios with the new engine, and design for the final drive with an average speed of 45 miles an hour.
As we said before, a lot of these improvements are good, but we've done a lot of work and we have low masses as it is. To improve on that and keep our masses down and even to reduce them some, we get into high costs because of low tolerances and other manufacturing deals. So we're looking at anywhere between $7,500 to $10,000 for the 2014 drivetrain, just to keep everything good. As far as spring 2013, we need to keep testing. Ideally, we want to look into having a chassis dyno, whether it's in-house. We need to make it efficient and make sure that we can trust what our results that we get there. That makes it real easy to get the overall driveline efficiency. The other thing that we can look into is once 2013 cars on the ground and 2012 cars freed up, if we have friends, sponsors, people that have a chassis dyno and are willing to run it for us, if we can ship it off there, drive the truck and trailer down for a weekend, whatever, a day, just to get that, as long as we can continue to test and we have a car to run back here, that would be great. The torque telemetry was a big thing, and we'd like to keep working on that and figure out how to get reliable, accurate data, as well as just making sure that we have enough power to power all of the sensors that we have and be able to design for our specific car. For simulation, as I was saying before, we want to integrate all of our simulation into Simulink, SimMechanics. MathWorks has been very generous in giving us a lot of software for free, so we want to take advantage of that, use it, and integrate it with the rest of the sub-teams, because we're all getting to be very interdependent. For NX modeling, because we have an evolutionary design, we want to take all of the NX models and parts that we've had previously, make whatever updates we are to them, or if we're not changing the parts too much, put them over and really get a jump on the NX modeling, see if we can get a full car model to 75% by the end of this semester. The design binders are a big thing in being able to bring new members up to speed, keep what we have and learn from our mistakes. That's been problems in the past where we start to make mistakes, the same mistakes over and over again, and really being able to have one document together is great, working with the seniors this year and hopefully keep working with the recruits and keep a current knowledge base up to date. And that'll help with getting all of our parts sized and ready to go. That goes hand in hand with the next modeling. And we need to keep making sure that we're helping out the seniors this year. We are one team, and even though we have a lot of work to do on the 2014 car. We've got competition in May, and we're not at, our car isn't competing in May. The 2013 car is, so we need to make sure that we don't ignore all of the seniors' needs currently. Any questions, comments?
One quick question, comment, because I've seen this happen the last 3 years. I didn't see anything about how you're going to act.
So we can contribute to the whole car model. Our main focus is focusing on the carbon chassis, integrated composites, and possibly carbon control arms. That will give us a lighter weight and a stiffer. These are some overall design goals. We are going to build off of the 2013 car. It has a really reliable performance, and we're trying to keep it that way. We are trying to integrate the air loads. 2013 is the first car that is doing a full aero load, so we are trying to test a lot of that and work off of that. And we're also going to reevaluate the overall vehicle specifications. Our drivers aren't Formula One professional drivers, so we have to design a suspension that can keep up with that success. Here's a list of the parts of the suspension and our design parameters. We are trying to design for a stiff and light suspension and have a high fatigue life.
All right, so for 2014, I'm continuing my work on 2013. We're going to probably upgrade to a new tire package. Preferably, I'm looking to go to a wider tire. Hopefully here we'll upgrade our overall total capacity for lateral acceleration. So what we're doing is optimizing the tire selection for the new aero loads. These are going to change our temperature ranges, possibly our warm-up times, choose a compound that's apt to that. We'll still use the full 10-inch diameter wheel, so the same rolling section diameter. So the Hoosier tires are most likely going to be the choice for that. We'll also greatly utilize the 2013 tire or testing data and the tire data from the outset. That's sort of a correction from 2013, since we didn't exactly start with the tire data, since Jeremy has finally gotten that up and running this semester, a little bit late for our full design of the 2013 package. And also integrate the model of the tire data in sim mechanics for a full vehicle model. So for the springs and dampers, the stable handling goal, this goes all the way back to creating a consistent, very drivable vehicle that is easy to get up to speed for novice drivers, learn the vehicle, and so forth. And here, the biggest thing to improve confidence in the drivers to minimize load fluctuation across the tires. When you either have cornering, pitch, roll, you have a bump in the road, something like that, you don't want to reduce the load on the rest of the tires. So here we try to reduce our overall wheel race and optimize our springs and dampers. However, we're limited by, especially with the aero package, controlling our attitudes and angle of attack, ground effect, and so forth. Now with an unsprung package, we don't exactly know quite what we're getting into. However, hopefully with a lot of the testing that we're doing in the 2013 spring semester, we'll get a much greater grasp on that. And also optimize the suspension frequencies for that aero package. They're likely increase. However, it requires quite a bit of testing. And also, we'll use on-track testing data for the dampers and at the dyno as well. So for the vehicle, we need to determine damper selection first. This will define a lot of the parameters in the suspension design overall, especially with our installation ratios. Likely, I'm going to continue using the Öhlins TTX 25s, revalved just like what we did on the 09 dampers from that year, which we're using on the 2013 car. This way we can use current development data directly into that model. And the valving should be reasonably close, and if we need to swap in and out for reliability or any issues that we have with dampers, we can do so. So the key interactions here are aerodynamics, the chassis design, bell crank design, ARB design to interact with the suspension and the spring and damper package, and also the control members, control arms, push rods, pull rods. We'll utilize much of the data from 2013, like I said, on the 2014 vehicle, and continue to model and increase that modeling prowess in sim mechanics so we can get a full lap simulator going up in the next year or two.
Alright guys, so I'm going to talk about the control arms. I brought a few props with me. My biggest thing is I'm thinking of switching to carbon fiber versus steel. And obviously, I mean, I'm sure a lot of you guys have seen this stuff before, but when you put it next to each other, it's pretty impressive. I'm thinking in the tubes alone, we could save 50% of our mass. On the system as a whole, 20 to 30%. So there's obviously a lot to be gained, not to mention the stiffness and strength is to be gained there as well. Of course, that comes at the cost of monetary cost, and it's going to be a huge testing and development push. We're going to have to be able to make sure that the reliability doesn't suffer first and foremost. Because if suspension fails, then it's game over. But it's going to take a lot of bonding knowledge, and overall, we're going to have to figure out the aero loads. There's a lot that's going to have to go into making sure that we don't lose anything over what we're going to gain in the weight and stiffness department. So that goes for control arms and pull and push rods. So obviously, as drivetrain mentioned, aluminum is pretty finicky when it comes to bonding with it. The bonds deteriorate. If that doesn't happen within our 100-hour fatigue life window, then that's good. Steel, a little bit less so. It's easier to work with, but there's going to be a lot of the big cost with this potential switch would be going to the research side of it, not necessarily the monetary cost. But that's where I'm at right now.
For bell cranks, we plan on doing an evolution of the 2013 design with probably no radical changes. One of the major things we're going to have to figure out is the installation ratio, because that has a big effect on how all of the suspension components work with reaction to each other. We also anticipate that we will be machining them out of aluminum, because previous teams have done research on this and it's shown to be a very good material for the bell cranks in the past. The anti-roll bars are also going to be an evolution of the 2013 design. They'll probably be designed later on in the process, only because a lot of their dimensions are determined by other dimensions with the chassis. Some of the things we're going to have to figure out are the sizing and the material for the torsion tube, as well as the mounting locations for the bar as a whole. We're also going to have to do some research on how different stiffnesses of the bar affect load transfer through the corners, so we have a better understanding of our system. Also, adjustability is key, because an adjustable anti-roll bar makes it much easier to make small handling changes when you're at the track.
Okay, for uprights, our design goals are basically the same. Keep the weight low, cost low, and improve stiffness, camber compliance, and bearing efficiency. One main new thing for 2014 is we're going to try to put the aero packet or aero loads directly onto the uprights. That's going to affect the design majorly. Going to have extra mounting points, and that'll affect size and weight. And for materials, we're going to look into aluminum, because we might be able to get PCC to cast the parts for us for free. But that's a very costly option, so if they can't do it for free, we're just going to stick with steel. That's been proven good design in the past, and it's really cheap. And it just requires a lot of labor, so you need a really good welder for that too. But if you can't get aluminum, we'll just stick with steel. Bearings, probably going to stick with taper roller bearings. That's just been proven in the past, and we can get those for free also from Tipton. And especially if you do a carbon suspension, you want the uprights to be really good, because if they fail, this will happen.
Alright guys, my name's Juan. So one of the major design changes for the chassis in 2014 is integrating composites into the steel space frame. The reason for doing this is that it will improve some of the goals and considerations we already take into account for designing the chassis. So some of those goals and considerations are the separation of chassis and suspension frequencies. This separating the chassis and suspension frequencies leads to a suspension system that's more sensitive to tuning changes, which also leads to a higher stiffness to weight, keeping stiffness constant, or it's what we need. It doesn't need to be excessively high, but keeping stiffness high while still reducing weight. This all goes into aiding tunability of the system. And then another goal is changes is fatigue life. So carbon is said to be a little more fatigue resistant, or more fatigue resistant than steel. Incorporating the composite panels into the steel space frame adds load paths, hopefully increasing fatigue life, avoiding something like 2011. One of the biggest considerations and goals, I think, for this, from this change, is the establishment and the improvement, the serious establishment of integrating composites into the chassis and developing it further. We've had composites in 05, 07, but it never went any farther than the year it happened. So increasing and building upon what we will start in 2014 with composites.
To go off of what Juan says, the basic concept behind that is making the tubes thinner and wrapping them in carbon fiber and still get the same equivalency as if we would have two thicker tubes. So why carbon fiber? We're designing a car that should be light and stiff, and carbon fiber is lighter and stiffer. It also has a high fatigue life, and we can tailor the loads pretty well. I wrote down the costs to show you that it's actually not that much more expensive. We have the opportunity to get our tubes laser notched for free with a very kind of local company. So instead of shipping them off to Canada, we can just buy the tubes and bring them there and get it done. That will save us $1,500. And that money we can spend on carbon fiber and the foam or Nomex honeycomb, depending on what we will use. We still have to decide that, and it will probably have some changes in the costs. So the total cost will probably be around $2,200, which is actually the same price as if we would ship the tubes to Canada.
Okay. For the suspension geometry and suspension dynamics, what we're focusing on is just small changes from the 2013 car. But some of the most significant changes that we might make have to do with the carbon control arms and as well as the aero loads. But what we're focusing on is to optimize the geometry for drivability and reliability. We're going to look at the ARM points and lengths, camber angle and gain, and ideal caster angle. Obviously, for the camber angle and gain, too little or too much, we're going to have some understeer. We just want to find the ideal angle so that we can get maximum grip, so we can do well in the skid pad and do well in the acceleration. For the caster angle, if we have a large positive caster angle, that'll give us more camber gain if we need it, but at the cost of having the driver have to apply more force to the wheel to turn it. And for drivability, that's an issue. And for the carbon control arms, we may need to do possible revisions for the geometry. Obviously, if we're going to change the geometry, we don't want to do something stupid like mount the push rods on the A-arms. Just no. And for that reason, it's because we want to avoid bending for the carbon fiber, because whenever you have bending, it's extremely brittle. So if it yields, at yielding, it breaks. That's not reliable. And adjustability issues. If we use carbon fiber, it's not like steel where we used in the past. On the 2012 car, it actually has a threaded A-arm connection and some threaded other connections so we can adjust it. Can't really do that with carbon fiber since it's going to be epoxy to aluminum or steel. I was thinking about doing something with the uprights, maybe having some adjustability there. And for changes in the geometry, we may want to accommodate a wider tire, and that may incorporate reducing the angle of the A-arm so that we can just fit the tire on there. For the kinematic portion of the design, big portion is to incorporate the aerodynamic loads into the 7 degree of freedom model so that whenever we make the suspension geometry, we can actually model it. And we need the tire data because we're incorporating a wider tire. So after we do the kinematics, we need the loads. And then to do this, we do an optimum kinematics.
For steering, I want to build off our current design and maintain its state of reliability. 2 areas of improvement are in drivability and performance. I want to make sure that our novice driver has as much feedback as what's going on at the front tires. So that involves reducing slop and compliance, but I don't want to go as far as making the steering so heavy that the driver is actually becoming fatigued. I also want to look at making our steering more linear. The use of U-joints alters the angular velocity of the steering shaft. I want to look at different configurations where I can reduce that effect. Also, in the past years, we've been kind of all over the map as far as Ackerman. And with tire changes, I want to reevaluate that and find out what I believe is best. To get here by May, I want to complete both a kinematic and a dynamic model of the suspension of the steering, and use that to determine loads and sizing my components.
So now, we all want to make sure that it works well in the computer and in the lab, but testing it on the track is a huge issue. One of our goals is to have at least 50 hours of drive time. That means on track doing testing that we can use at competition. So that has to mean that everything is ready to go, and that's first done by completing pre-drive. Everyone has to complete their pre-drive, each subsystem, as well as every team submits requests for what they would like to test on, and that's also incorporated in pre-drive. There's also structural testing, which, can you go back? Which, with the new aero loads going into the chassis, those are going to be tested, and that's done by using strain gauges in a Wheatstone bridge formation, and the changes in this out are used to determine the strain that's new to the car. Another thing I want to implement is traction control, and that's done using the Motec 400. And this takes wheel inputs from the track and determines how is this differing from what we're expecting from the engine, and adjust the engine accordingly. One of the big things to do is to just change engine timing, and that's the best way for us to go, in my opinion. Then another thing to adjust is the 7 degrees of freedom model, which was developed by an FSAE alum, Chris Farabee. And currently it's modeled in Simulink, but most of it is all road inputs in this block, and it doesn't account for any of the new aerodynamic loads that'll be coming from there. And so while adding the aerodynamic loads, I'd like to change this from Simulink and MATLAB to SimMechanics, which is a lot more user-friendly because it's all based on springs and dampers and not doing the state space or transfer functions correctly.
Here's an overall cost estimate for the suspension sub-team. We're going to need a new set of dampers, which is going to be quite pricey, new tires, and then the chassis. We have an estimated cost of $10,400, but that is very likely to change around. So what are we trying to get done in the spring? We are going to establish a gain chart, and we're going to try to follow that as best as possible. We also have a half-scale chassis that we would like to build and get some testing done on that. We want to do lots of testing and design our stuff in FEA, and of course get it done, have it modeled in NX and Simulink. And one of our main goals is get the chassis at least the tubes laser notched during the summer. Any questions or comments?
Back to the first slide.
Yeah.
Which slide?
Whatever one started the subject. And we'll just kind of go through them. This is, I'm gonna waste your time with this question. How much wider?
About an inch.
So we had, what, 6 inches, and now we're going
7.
to 7? Or was it 8 inches? Anyway, we're going to be sharing tires, that's what I'm going to say.
Okay. Good.
New aero loads. This is a question for your whole sub-team. What, define new?
As far as are you talking about for 2014 or 2013?
Yeah, I mean,
In
is it
general?
just, where's the new coming from? Does everybody understand?
The wings,
New
front
aero
rear wings.
on 2013, and then 2014 we're trying to put them on the
What kind of aero loads do we have in 2012?
Zero.
No, there's
Really? Really?
There's the diffuser.
Yeah.
We could make 180 pounds at 80 miles an hour that you never see at competition. So the aero loads have been defined, and we'll go through the details later. Just, it's not a new thing. Don't be worried about it.
I had a question. Do you guys have tire data currently?
Yes.
Do you guys use it?
Yes.
Okay. Yeah, that was one big thing in the past that we always had problems with. And that
We are the 2013 team as well as the 2014 team. We have been designing for the 2013 car for the past couple months, and we also are looking forward as the 2014 car. So the main goal of the aerodynamics, if you're not familiar, is basically just to increase the cornering speed. We're trying to generate lift at low velocities so that the car can have a faster turning rate. But this does come at the sacrifice of drag and top speed. So this will be the second year with the car's full aerodynamics package. Right now, the wing sections have been chosen and they're pretty much set, and we are still working on the diffuser and the body design for this year. Right now, we're developing around 131 pounds downforce of 35 miles an hour. That's our maximum load. We can tailor that down so we can decrease the angle of attack to suit the driving needs or whatever the chassis says we can do. And our next goal is to manufacture. So the big thing with 2014 is we're just going to fine tune the aerodynamics around the car. Since we have such a short time to design the 2013 package, we know that the wing sections might not be optimal, the spacing between them might not be optimal, the placing might not be optimal. We haven't had the time to think of all those things. So that's what we're going to work on for the 2014 design. We are also going to increase our design velocity. This year we were designing for 35 miles an hour average cornering speed. Since recently the tracks have been getting faster and more emphasis has been placed on aerodynamics, we are going to increase that speed 10 miles an hour to design for 45 miles an hour instead. One of the other things we're going to focus on in 2014 is just to improve our design cycle. Since we have experience 1 year, we're just going to try to basically improve upon that experience in the second year and just do a faster design cycle and more productive design from that time that we input into it. So the preliminary size for the 2014 car will about stay the same. The wings will about stay the same general size and in the same general placements, albeit a couple inches up or down or backwards and forwards. The diffuser might get smaller in order to reduce weight, increase effectiveness. I'll talk about that later. But right now, this is the estimate for the entire weight of the package. Some of these things, like body and side pods, have traditionally been the suspension weights, so we are taking upon them. But overall, the weights are shown as around 60 pounds. And that's the other thing with aerodynamics. We are adding weight to the car, and this is weight we have not seen in the past. So we are adding weight, increasing drag, but we're trying to increase the cornering speed as well.
Alright, so for the wing designs, currently our 2013 goals were to produce 45 pounds for the front wing, 55 pounds for the rear wing at 35 miles an hour. And with our current design, the front wing, due to ground effects, is able to produce 58 pounds of downforce, while the rear wing is able to produce 45 pounds. So with that 2013 design, we're going to have to tailor the front wing so that we can keep the weight distribution at our goal of 45% created by the front wing, 55 by the rear wing, to improve drivability. And then our 2014 goals are to increase both the amount of downforce for front and rear wing, as well as increase the overall efficiency. so keeping the drag at a reasonable level or possibly decreasing it. Then for the front wing design, like I just said, we're able to produce 58 pounds of downforce. And the location right now, we have it at a 1.5 inch ride height, which is the height between the ground and the bottom of the end plate. And some improvements we're looking at for the 2014 design is to improve the interaction between the wing elements. Since we're going to have more time than we had for the 2013 design, we're going to look at placing look more closely at the placement of the second element, just to see how we can tailor the flow to improve the overall numbers. Also, we're going to be looking at, for the front wing, the nose of the body has a huge impact on how effective the front wing can be, so we're going to look and try to improve how those components work together. And a big thing that we're going to be able to, when we're doing on-track testing this spring, hopefully we'll be able to learn a lot about how that actually works, because it's difficult to model in CFD. And also we're going to look at airfoil shapes. As far as looking at the first element, we think we can create a design that produces less drag and relies more on ground effects to produce the lift that we're trying to achieve. And then also we're going to look at how the wing can reduce the drag on the front tires to help with our overall drag numbers.
For the rear ring, right now, we're looking at about 45 pounds of downforce and 9 pounds of drag. We actually have one more CFD test to run with this same wing profile at an increased angle of attack, so we'll be looking at more downforce and also more drag. Location-wise, we have the leading edge at about the top of the driver's head and the beginning of the leading edge at exactly the midpoint of the rear tires. We want to get them as centered over the rear tires as we can. The end plates take about as much volume as they can within the constraints of the rules, so they can't go past 1 foot behind the rear tires or above 2.7 inches above the rear tires. We know that bigger end plates are really efficient at decreasing drag, and for the 2014 design, we want to iterate off this. We're hoping to learn a lot from this spring, from actual on-track testing or wind tunnel testing, so that we can verify our location and our downforce numbers. One of the big things we want to do for the 2014 car is design for adjustability. We know that the rear wing is going to have a large amount of drag, and because of its location, it's going to create a severe moment about the center of the car. So if we can reduce that drag in between different events, so for the acceleration run, we want as low drag as possible, where downforce doesn't really matter. So we want to be able to adjust at least the second element to maybe a 0 angle of attack where there's minimal drag. So that during the acceleration run, there is no drag in the engine. It's not strained nearly as much as it would be during the endurance run or autocross or something like that.
Alright, so I'm designing a body for 2013, and we're going to be iterating off of that for 2014. In the past years, the body changes a lot every year, and we're looking at trying to get a very low drag body and not have it change as much every year, because we're trying to get a very nice design. So what seems to be best right now is a step nose design that's shown in that picture. The other nose configurations seem to mess with the flow over the front wing too much. So having this step nose allows for better flow over the front wing, so we can get more lift from that. In 2014, I want to look into an integrated impact attenuator into the nose. That will allow us to have a more dramatic step on the nose and a narrower nose. So it will allow for even better flow over the front wing. I also wanted to look at putting a windshield
or similar thing on the front of the car so we can get the air going over the driver more. So right now, the air is crashing into the driver's head, causing a lot more drag. I'm also working on the side pods. We don't have very much done as far as design on the side pods right now, so that's going to be our next big step. We really want to get the best flow, a lot of energized flow coming into the side pods, slow it down to the right speed. We need to talk to the engine guys, figure out what flow rate they want going through the radiator so we can determine the size of the side pods. And then we have to figure out where we want the flow to exit, whether we want to energize it back to free stream and try and reduce drag, or if we want to send it over the engine and help cooling it all. We also will look at putting any things lifting up on the side pods to get the flow going over the rear tires to help reduce drag from that.
For the under tray design, on the right is shown the current 2013 design, and on the left is something similar to what I want to do for 2014. On the right you can see we're trying to do some kind of intake and exit design this year. This is just to try to increase the effectiveness of the diffuser. Right now we're getting about 32 pounds of downforce at 35 miles an hour. The main issue I see with the 2013 design is just the size of it. We're not sure if we increase, or right now the design's pretty much maxed out to the biggest that we can make it. And we're doing this just to produce the maximum amount of downforce that we can. However, that might not be the optimal setup for the weight that we put into it. So if we want to decrease the overall weight of the aero package, we have to decrease the size of our components. And we might find that in decreasing the size of the under tray, we still retain a lot of the benefits from it, but lose weight. And that might increase the ratio of downforce per weight that we're adding to the car, which is an important ratio for competition.
Okay. So I'm the poor guy designing all the structures for the aero package. So the current design that we have is actually based off another car model that we really liked, and that was Monash's car that we saw. And you can't really see the elements too well, but there are two vertical bars running up to hold the wing. And I really like that design because it's basically going to allow for the center of pressure of the wing where all the force is going to act through to be between those two bars and going to really decrease the bending and the moment loads from that. And it also has a couple of lateral bars being attached to the front of the wing, which is really going to help us in turns and sort of translating the force into the chassis that way. So what we want to do is really make sure that we're transferring these loads correctly and making sure that we're receiving as little bending in the wing as possible, because as soon as the wing starts to bend, then we're going to lose the properties that these guys are designing for. So what we want to do is use some sort of river spar system inside the wing, which we're looking at different possibilities for now. So really the material we want to use for that is foam and rapid prototype, possibly aluminum, depending on the type of, or the amount of load that we're going to see. We also have to look at manufacturing, because obviously this is something that we haven't done before, so I plan on being here for a few weeks over winter break. And front structure design is something that we're just beginning to look at now. Like I said, like we've been saying, the aero team is a little bit behind for both this year and next year, but hopefully after we get this year's design down, over the coming weeks we'll be pretty much set to iterate for next year. And we have some numbers here at the bottom. The maximum load that we would like to see is 220 pounds, and that's just for the rear wing at 70 miles per hour, which we anticipate being our maximum speed. And we're also doing some initial side load calculations, and we got a 17-pound force from that.
Alright, so a big thing with the aero package is how all the elements will interact with each other. So one of the biggest problems we're facing is how the moment arm for the rear wing is a lot smaller than the moment arm for the front wing. The car wants to roll forward, so we've been doing a lot of MATLAB simulations, mostly statics right now, trying to work into a more dynamic problem. And we're hopefully going to be getting into Simulink, trying to model that. We have code right now with all of our aero forces. Any of the sub-teams can access it, and it should be pretty easy to understand. If you need any of the aero forces, you can get the forces from that. Then we have our calculators to figure out the moments. You put your velocity, how fast you're accelerating, and the turn radius. And that's, the code up there is a sample output of what we're getting. I think that's 35 miles an hour, has our moments and forces in each of the axes.
Right, so testing is a big part of aerodynamics. We can't discover what forces we're putting on the car without testing. The biggest tool we've used for that currently has been CFD. The current package we're using is the Simulation 360, which is a cloud computing software. So we've been struggling with issues all this year on how to get quick tests done in the lab, and we've been having a lot of software issues. So Autodesk has this, basically it's a cloud computing. You send it out on to their servers, and their servers do the computing, and then basically we just get the results back. So this kind of decreases the testing time that we spend in CFD. One of the things we did last year, and we're going to continue doing this year, is testing in the OJT down in Randolph. The OJT is the open jet wind tunnel. So this isn't a closed wind tunnel, but it's open to free stream air. We want to, we'll want to rerun the calculations done in 2012 just to make sure that we verify. But also we're looking into doing possible scale testing of our wings package for this year, so that we get experience with that and we can iterate off those designs for 2014 and do that quicker. And we also might have we might have a possibility of testing in a full wind tunnel with the 2013 car, if we can find a place to do that at. A lot of our tests are going to come from, a lot of the real world testing is going to come from on-track testing, and we're going to do this through the suspension potentiometers, which was used last year to verify our loads. But this year, since we have wings, we can also use strain gauges to verify exactly the loads that we're putting through those members. On-track testing will also start flow visualization to see where we have flow separation, and stall if we have stall on the wing sections. And we can also do that on the diffuser. And as well, as Andrew pointed out, Ohio State tests their front wing just by impacting a cone. So we'll do something similar to that, just to verify that we have the structural rigidity for our cone, if we do get a cone for competition. Spring 2013, we're going to start manufacturing for the 2013 car. Final analytical analysis for 2013, and that will include hopefully some wind tunnel testing in there, just to make sure those models are accurate. And over the course of the spring, we're going to try to develop more kind of quick 2D codes that we can use for not only airfoils, but for the diffuser, and also to get the loads through the rest of the car through the moment calculator. So.
Before we get to questions, I just want to talk about the cost. There's no slide. The majority of the pricing is just going to come from the carbon fiber alone. The foam is like $30 for a big sheet. It's not really that much of a problem. The steel, we're estimating about 15 feet. So that's going to be a little under $100. So the whole thing is a little under $2,000.
Any questions, comments? Yeah.
Also, Eddie, I ran the test. The new one with the increased angle attack is running about 60 pounds with 11 pounds of drag. So.
Hey Brandon, where are the MATLAB files for the forces and elements?
Under the air
power that each of the elements will draw. What we'd like to do is find a real-time power analysis. This way we know what each part draws at certain times. That way, if there are overlapping power draws, we know that we'll still have enough. And if we're able to do a real-time power analysis, that'll definitely help our whole understanding of the power system. We're going to do this through data testing on the rolling dyno. This will be the easiest way to simulate and understand how the whole thing works. The biggest thing we'd like to do is work on complete modeling, which we don't have. We'd like to do the total power system,
but especially the stator, which we know what the max power that it can generate. What we don't know is how it operates at each input frequency, which is really important for us. So modeling is a big thing we want to move forward towards. For the 2014 car, because the 2013 tasks we're a little bit short on time, for 2014 I'd like to complete the remainder of what we have, mainly the modeling. The big thing that we as a whole electrical sub-team want to focus on is reliability. And a big way we can do this is through weatherproofing, and this includes just waterproofing it. Also, a lot of the vibrations, we want to make sure that when the electrical parts resonate, nothing falls out of place. That's a big thing we want to look into. And then, based on new elements that will be implemented for the 2014, we need to make sure that we will have enough power. So that's the big thing we want to work on.
For wiring, since it's evolution of the 2013 car, Carolyn has set up a system which the 2014 car will also use, just to make sure that people who are not familiar with the 2014 car but have seen the 2013 car, it's the same thing. The wires are going to be labeled the same way. The layout is going to be similar, make sure there's no rat nests and stuff like that. But just so when people see the wires, if they know the system, or they can easily get acquainted with the system through the table, they can follow and make sure that it's nice and neat. And yeah. We're going to try to eliminate human error. Caroline's starting with just having different connectors. There's also the idea of on a certain, like if, for example, the battery, you'll switch the male and female connectors. So you have to put the male into the female for positive, and then the ground would be reversed, so you can mix it up, which I heard there was one time there's a problem like that. So just to make sure to eliminate all human error, we're going to try to manipulate the system so it's practically impossible to mess it up. We're also, the 2014 car is going to stress on shielding wires, not only in the high voltage areas like the battery and other components, but just throughout the car as much as financially possible. It's to protect and just to make sure that there's no outside damages to, or just, yeah. Also, the big thing we're going to do is we're going to move from fuses to circuit breakers. We're going to, because it's first of all easier to reset if there is an error, because all you have to do is flip a switch, not find a fuse. And then we're going to set them up throughout the car to make sure it's easily, you can locate where the error occurs. And so breakers are going to be the big change.
So the big thing for electronics is focus on reliability and diagnostics. In the past, there's been quite a bit of work done in reliability with the power distribution unit and brake lights. For the power distribution unit, it's been reconfigured to prevent internal destruction of components, which is a big deal. And the brake light has been moved from a series circuit to a parallel circuit, which drastically reduces the chance of complete failure in the brake light, which would not be fixable. For diagnostics, a big move that last year is doing is putting onboard status LEDs on the PDU, which will allow diagnostics and pinpointing of what's working and what's not. So for the 2014 plans, it's an iteration off of 2013. We want to take the reliability and diagnostics further. So one of the reliability things is what Mark was talking about, weatherproofing. Make sure everything is water resistant and isn't going to be damaged by vibration coming from the car. And this can be done through casings or coatings. This has to be looked into a little bit further to see the best way to do it. And to take diagnostics a step further is to go from the onboard status LEDs to the possibility of wireless diagnostics, shooting out to a computer that something is wrong rather than having to look at the board itself to see if something is failing. Another thing is, like Mark was saying, we don't have hard numbers for power budget and real-time analysis. So there's a sensor that was proposed by an alumni, David Hatcher, that wasn't implemented because of his time constraints that I really want to look into putting into this car. This would allow us to get real-time values coming out of the battery to make sure that everything is going
how we planned it to, and it would also take out a lot of the guesswork that we're kind of forced to do and make sure there's more design in the process rather than assumptions.
Alright, so my mentor and I implemented a way to gain direct access to the Motec through the use of the CAN bus and the Cerebot microcontroller. So instead of being handcuffed to the software provided by Motec, we can now create our own software and hardware to do things such as onboard diagnostics. So if the engine temperature got too high, it would light up a red LED and be like, stop running the car. Other things like the battery voltage too low and other things like that. And then further improvements upon that, I plan on implementing wireless communication between the Cerebot and a laptop. So we would be able to have off-board diagnostics and wireless telemetry. So we would be able to have a screen just like the one here, which shows RPMs, throttle position, sensor checking, all while the car is actually moving. This would also allow for instant data acquisition. So instead of doing a run and having like data logger on the car and then pulling it off after the car makes the run, we would be able to instantaneously see if we're getting good data and stop the car, fix the sensor or whatever we had to do to actually get the data we needed.
So as many of you know, one thing that Electrical's been doing this semester has been researching an electrical powertrain to debut alongside the combustion car in 2015. And what you see here is the motor that we have selected. It's the AC propulsion in 75. It's about 10 inches long and 12 inches in diameter. What you see pictured here is a cooling shroud that will be a little different because we'll most likely use liquid cooling. But it has 100 horsepower peak, 13,000 RPMs, 90 foot-pounds of torque, and greater than 90% efficiency. And it weighs about 80 pounds, which is pretty comparable to the combustion motor. However, it's going to need batteries to power it, and these are very heavy, so we needed to have extra power to compensate for the extra weight that we're going to pick up in the batteries. A little bit about the batteries. We are going with a lithium-ion nanophosphate battery, and the main reason for this is safety. Some of the lithium-ion metal oxide batteries have failure modes of igniting or combusting, and this would be very bad. So we're going with these. These batteries are rigorously tested, and they're extremely safe. You can drill through it, you can smash it, you can draw too much out of it, you can overcharge it, and you might break the battery, but it's not going to act in any harmful way. The other good thing about these batteries is they're very power dense, so they are lightweight for the amount of energy you can get from them, which is really good for us since we're going to need a lot of them. And we're looking at around a 7 kilowatt battery pack that would most likely be split into 2 pods like this, but a little bigger and packaged a little differently.
So one of the big things we want to do with the electric powertrain is we want to kind of bridge the gap between the two cars. Right now we're kind of unsure of which different parts are going to go and like what we can reuse because of the weight and the extra torque. So by further researching and testing, we want to kind of bridge the gap and kind of have a lot of similarities between the two cars. So the kind of spring plan for the electric powertrain is move on from the research and kind of begin testing, kind of get a feel for how the motor works and stuff. Big thing for that is we need to kind of get sponsors and stuff to help pay for the costs of the electric motor and the batteries. They're not cheap. And then from that, once we get hopefully electric motor at least to start testing on, maybe from the power lab or something, we can take it to the dyno and test and see how it starts to work so we get a better understanding of it. A big thing we want to do, and it's kind of been emphasized throughout this, is modeling it. So we want to model the electric motor and sim mechanics and kind of see, using like other data from sub teams, how it's gonna, like the extra weight and the extra torque is gonna affect and make it better. So this is just kind of the cost estimates for the combustion car, kind of based off the 2012.
Any questions?
Hey, Natan. And maybe we'll do it this year too. But for the breakers, for the circuit breakers, however many there are, if there's 1 or 3, make sure the driver accessible. So if we're on the line at endurance, something fails, we still might be able to run, and the driver can hit it again, and if it's accessible there.
On the same slide, is there going to be an increase in weight with switching a lot of them to shielded wires, and do you know what the relative weights are?
I don't currently know the relative weights.
Because it could add up pretty quick.
Yeah, that would be one thing to find out soon.
It
Yeah,
will, don't let it hold you back though.
Yeah.
This, you're all going in the right direction, so if you have to gain a little bit of weight now to lose some more later, do it.
Yeah.
One thing on the telemetry, Bryce, make sure we have the backup USB, you know.
Yeah, that was definitely the plan. We
If
have
the
two different.
telemetry goes down, I don't wanna lose any data. You know, so what we're doing by now is make sure we got that. Always, we need to have basic capability. Getting fancy or making things a little more effective is good, but basic is fundamental. Make sure that we don't lose that in the process.
Is your PDU fully potted, or is it just coated?
I'm sorry?
Is the PDU going to be potted, or is it just going to be spray coated to protect the board?
I'm not really sure. That's something
In the past, it hasn't been coated. We were talking about 3D printing bodies for it, or casings for it, but there hasn't been much. Well, there was a lot of post-manufacture work done to it, so it was never finished in the sense that it was finished with like a coating or anything like that.
Yeah, you guys were talking about weatherproofing and just reliability. Making it potted makes it a little bit more durable.
As the guy who wrote up about 60 failure reports last semester, this human performance prevention thing is a really big thing, and I want to give you kudos for that. Also, with your onboard diagnostics, and I don't know if you're having any auto shutdown or type of thing going on, just consider about what you're doing when you do that and whether you need to actually shut down the car or just a certain system, because it's also not only just a competition thing, but also just from the nuclear industry. And you'll understand that I see a lot of bullshit at my job, but so one team had just kind of said, all right, we're just going to shut down main power, and sometimes that's not the right thing to do. It can actually make the situation worse, so just keep that in mind.
Yeah, auto shutdown's great for making sure someone's going to be safe, but in the event that nothing's going to blow up or hurt anyone, you do want to finish the race. So
We didn't plan on implementing an auto shutdown. It would be a user.
Okay.
Just the driver would be like, all right.
That's fine. Don't think it too complicated. You got a lot of good things up here, and like Dr. West said, keep it simple and just kind of get something, a starting point for learning. That's usually your best investment.
Is heat an issue?
That's one thing I forgot to impress upon you guys, is that especially with the power stuff, is that a lot of it, when it does a lot of the regulation and stuff like that, it does generate heat. And like my plan is to have it in the side pods that the aero team talked about. That's where that stuff is going to be for, so it has proper airflow to get cooled. Because right now, all of the electronics are shoved under the seat in the 2012 car, and then, I mean, the regulators on the back there are mounted to the chassis. But all this other stuff, that needs to be mounted in side pods for air cooling.
Yeah, that's one thing that you guys should, I mean, I know you're still conceptually designing things, but as you're speccing components, one critical thing that you should put a checklist to look for each component is its temperature range. And if you see something that has like 100 degree or 120 degree, I mean, don't put it anywhere near a 108 degree engine. So good luck on that, right? But seriously, that is something you need to consider, because if sensors can operate 150 degrees, it might be for a specific time, and then they just fail. So keep that in mind. And like you mentioned the fail-safe sensors, like if your water temperature or things like that's. You'll have to, you liaise with the engine guys or the drivetrain guys, and that's a really great idea. But if you're in endurance and you're at lap 10 and the water temp light comes on, and you've got 2 more laps to go, you need to think about, okay, how do we cool the engine down, or how do we cool it and still finish? I mean, it's great if the light comes on, but you don't want to, you don't want to know that, just I mean, see if you can engineer that in so the driver doesn't have to worry about it. I mean, you're that much of a better engineer. So
The one thing I want to mention is for the electric powertrain. I know Tyler and I were talking about it, but there's going to be a lot more safety to consider working with the high voltage system. And I was talking to Vinny about this yesterday. Actually, that includes training and new tools and PPE. So it's going to be, you want to include that into your cost as well, or find a way to get it for free
What
or cheap.
voltage does that system run on?
It's going to be, the motor will run at like 388 volts.
Is that something you guys have to go to, or is that something you are choosing to go to?
Electric powertrain?
Yeah.
We're choosing to. It's not taking away from the combustion car. We're going to try to do 2 cars to compete with.
Okay.
You meant the
Sorry?
the voltage.
Oh.
And did you mean?
No, I meant like, are the rules, do they make you, or in 2015, are they forcing you guys to have electric?
No, it's a choice.
Okay, so this would be 2 separate cars? Okay.
Yeah.
But yeah, that's something like at Oxford Brooks, I mean, that was one, an F1 or anything like that, I mean, it's, the electrical stuff is, if it's energized in any way, or even if it's broken and somehow it shorts through you, I mean, you could be looking at hospitalization or death.
Yeah,
So,
definitely. Yeah, we wanted to keep them alongside, like this showed that keep as many components the same between both cars that we can. We don't want to change sections unless we have to. Excuse me.
Don't forget HCBT is in Wear Lab 2. And
That's who we spoke to.
We've spoken with them some. Anything else?
Here you can just see a combined combustion analysis. This is very likely to change. It's just a really rough number that we put down. So in our spring, working on the business logic plan, this is something new that SEA has enforced us to do. So we're going to work on that. We're trying to get a Gantt chart set by the end of January, and of course get a lot of testing on the 2012 and 2013 car done, and then hopefully start manufacturing during the summer. Thank you everybody for coming out. We really appreciated it. Lots of great.
Go back to slide, one back slide. All the teams in 2014 have a chance, all the sub-teams have a chance to do something individually, and you should do this as an engineer, as a 40-year operating and research engineer, from explosives to dynamic situations starting in race cars years ago. Your Gantt chart, your individual responsibility to deadlines, your plans will end up in the reliability, the safety, and obviously VT's Motorsports reputation. Take seriously ownership in your Gantt chart, in your schedules, in your milestones. They slip, they're realistic, you encounter challenges that you hadn't financially or time-wise been able to manage, class load, all of those kind of things. But set yourself a goal personally and as a sub-team and as a team to be rigorous, even to the point of having a bad guy who's going to look at your Gantt chart and say you're slipping. And if you can get the 50 hours of testing, obviously you've elevated your whole program for 2014 into a whole mode where you talk about development costs, you talk about the reliability, getting the results. So that step right there that says scheduling, planning, and Gantt chart, take that seriously and take it personally. And Mark and others who've done the scheduling over the years, and I can attest to it, your reputation and your reliability and your results are as much as a factor of your planning and then your execution, but planning is critical. So don't underestimate putting together when the request comes in, the Gantt chart says, here's the deadlines, you take and throw it up there and you say, I can make that or I can modify it. That's true. But if you get the 50 hours and you'll win. If you don't get the 50 hours, and I'll hazard a guess, you're going to find, just like many teams have, we didn't think about that. Wow, 50 hours of testing. It makes a big difference.
Another thing I want to add to that is, as a team, you might want to sit down and do an FMEA of your things that are new or high risk, or just the whole project itself, and it'll
at the end of it, it'll pretty much key out the most important high-risk things, and you might want to, when you end up doing your Gantt chart, throw, a fudge factor on there that says, realistically, we're going to need 50% more time or something like that. It's a pretty useful tool for trying to figure out that.
Christian? Yeah, do you guys think you're actually going to be able to do 50 hours of testing? That's a lot of hours driving.
It's our goal too.
That's why I'm saying that. You think that you're going to be able to do that?
I think that's why it's important to do have a Gantt chart, to start it this semester, and then have it all next year, and be on people's cases about getting their stuff.
That was the whole point of getting it done by the end of January, at least a preliminary skeleton, because as we all know, during 4015 meetings and so forth, and Gantt chart updates were due last night, and I know not all of them were quite done, but we're going to have to work on that, and that's why we're trying to implement it early as a culture thing on the program rather than just an add-on to check the box. So.
Or if we don't meet a deadline, why did we not meet
Right.
the deadline?
Yeah.
It was, but we need to.
I just have a general question for the team this year, and it'll follow on you guys, is that what percentage would you guys say of your car is modeled in CAD? Is it 100%? Is it some?
Where would you say we are? We're
I would say
probably 70, 80, somewhere in there.
What's missing? Electrical and
a few of the
fasteners.
suspension bits, some of the really detailed stuff, and then some of the electrical,
Yeah, like
the wiring.
wiring, you don't need that. I mean, it necessarily, but like that's one thing that we've always struggled with in the past is not modeling things, and one thing we pushed in 08 was modeling as much as we could and trying to design a race car. And you wouldn't believe how many problems we solved and how much time we saved by properly modeling things. We caught so many kinematic issues with the suspension by having having a constrained model with playing around. It was a separate model, but it was playing around with where our max and min ranges were, and we hit so many things in the CAD that saved us time from wasting money and wasting manufacturing time. So I know that historically that's been a problem here, is CAD modeling up front to a detail like bolt, nut, washer, GD&T level. But for me personally, as a new, when I was coming up through the ranks in the years, is that those deadlines that you set for yourself, that you had to have a presentation, you had to have a model done for it, that was when I learned the most about CAD. So it's like these guys are talking about the deadlines and your Gantt charts and stuff, and you'll have to spend a lot of time on the learning curve if you're not experienced with CAD. But at the end of the day, I mean, you put out a design that you can make, and hopefully that everybody's design, you can look at it as a systems level and you can figure out how you can better integrate to make a lighter, stiffer, faster car, and then eliminate problems so that when you send it to manufacturing, hopefully you manufacture it once or twice, at the right time, and you go on about the next problem. So.
Yeah, we this year for 2013, we brought a guy on and put him purely on full car model management. Charlie couldn't make it today. He had another commitment.
And we're going to continue that in 2014 and really push for that.
Right. And have sort of a functional subgroup there that each sub-team would have their assemblies head.
Yeah, that's good that you guys have done that, because obviously that was a big failure in the previous years.
Yeah.
One more thing, has anybody gone back in the last 10 or even longer years and did a failure analysis of VT Motorsports design concepts and said, here's where our failure, just building off that, is it in timing, is it in delivery, is it in testing, is it in component, whether reliability? Obviously reliability is paid off, or it hasn't.
Right. Well, there's mixed and sparse analysis, at least from the competition. For example, from 2006 on, there are failure lists of why the car failed in endurance. Andrew tried to start, or has started, a failure reports that we're continuing to use. So we're collecting the records. However, there's not anybody right now going into and analyzing it. And part of it, the design binders that we're trying to do, and Dr. West, we've been trying to get that in there, is going back, looking at what's been done in the past, looking at what's been, and every time you analyze something, you look at what's been done in previous years to make sure you're either making an improvement or at least keeping something that worked the same if need be.
Are you guys keeping testing logs?
Testing
As
logs.
the team as a whole started doing it?
Yeah, we keep everything from testing.
Yeah.
We log everything as failures. All the aim logs are on the server. We keep everything.
I'm saying not just necessarily on the car, but like in the dyno, you have like an Excel sheet that says whoever's running the dyno came down today. We did this, something blew up or whatever. Just, I mean that's a huge amount of testing, stuff like that. Or even if you go to doing damper testing or something, in the future, someone, the design notebooks are great, but they get misplaced a lot. Something that can live on the server is somebody can go back in that, especially for someone new, maybe to running the dyno or whatever else.
Well, now we have a whole section for design binders on the server now, so that's part of it. But yeah, you're right, Johnson. About
it's
having
easy enough.
A whole master list of all the testing. Yeah.
I guess the other thing on the testing side, we're trying to look at 3 different levels on bench, lab, and then track. So that way everybody can come up to speed and do some testing on components or subsystem levels, maybe on a bench, some of them. But then it has to do with getting familiar with the sensors and instrumentation and everything before you actually get to put them on the vehicle and get them on the track. So you're moving that through the system. So that at this point, we are not recording for those levels, we are not recording what Johnson just asked.
Overall, I think it looked great. I'm glad we got you guys on track because we're kicking our asses we're getting our asses kicked for not being here last fall, and it really sucks. But you guys are doing great. One thing for everybody, when you say you're going to shave off weight, just have a good plan for it. Don't say it just to feel like you're really developing or say it to impress us. Like, I think with the aerostructures we were trying to keep it bare minimum, but we realized we'd much rather have it a little heavier and not have the wings rip off during competition. Like, just have a good reason why you're shaving weight. There's nothing, like they were saying, there's nothing wrong with copying design. If it works, it works. Just have the reasoning for that. I just know, like, drivetrain and engine, especially with the plenum, it's iffy because we blew up the plenum last year in the garage at one point. So, like, I don't know if shaving weight there is the best idea, but just have good reasoning for it. It doesn't mean, the light car is going to be best. Just keep that in mind.
Stevie, you guys are fantastic.
If you haven't noticed, you're all pushing in all these other areas, and as Mark said earlier, you got a lot of different trade-offs, and the games become smaller, and you're all still students in a mechanical engineering program.
Well,
there's only so much you can do, College of Engineering and/or business and some of the other stuff you've got going now. Time is one of those resources. Don't forget about it. And I know you're learning, so you're still developing your sort of perception of what time it takes to do something. So that's something that's also at a sub-team leader level. If you see somebody chasing a cavity to shave off a couple grams, put them on something else. And that all comes with scheduling, and you'll see why big companies spend lots of money on ridiculous stuff. So just persevere. We all have been in your shoes before. We know it's hard, so that's the learning you get out of this. It makes you a very valuable asset to an employer someday.
Yeah, very good.